The last time we were together, I kind of ended on a somber note and was discussing with you Social Security and how there are so many people that are pulling in checks from Social Security, not just retired folks, but many people for a variety of reasons are getting a Social Security check. It's to the point now where there's not even 3 people working for each person that is pulling in a check. Excuse me, and I mentioned to you at that time that we really need to consider, is Social Security going to be around for you folks when you are my age and ready to retire? Okay? Really a serious thought. What can you do now? What can you do now to be ready to retire if Social Security is still there, maybe greatly diminished? But I thought it was something worth talking about. So, how to prepare for retirement and the hesitation about Social Security.
Say you have a really beautiful home with some really annoying neighbors, and you want a nice tall line of hedges to give you some privacy. When would have been the best time to plant those hedges? 10 years ago, right? Well, since we aren't capable of time travel yet, when's the second best time to plant those hedges? That's right, today. Let's take a second and talk about procrastination, more specifically, financial procrastination, and how it could be costing you thousands, if not millions of potential dollars in retirement savings. We all know that time is our greatest ally in growing our nest egg. The longer you leave your money in an interest-earning account, the bigger that number can grow. But exactly how crucial is the need to invest early? Let's take a look. Larry and his twin brother Barry are both 19 years old. Larry gets off to an early start with his retirement savings. He starts contributing $2,000 a year to an account that gains annual compound interest at 10%. Larry sticks to his savings plan for 7 years, but hit some tough times at age 27 on a bad investment in hoverboard technology. He stops contributing after that, but his savings continue to grow at 10% interest. His twin brother Barry, on the other hand, is a bit of a procrastinator. He doesn't contribute anything for the first 7 years, but at age 27, he starts contributing his $2,000 a year and continues to contribute that amount every year through age 65. So where do our twin brothers end up at retirement? Well, they both end up doing pretty well, but Larry's got the larger nest egg, despite the fact that he only contributed a total of $16,000 compared to Barry's $78,000. So how is it that Barry invested $62,000 more than his brother, yet now has $150,000 less in his retirement savings? The answer is time. It's a beautiful thing, especially when it comes to compound interest. Let's look at this another way, and at a more conservative interest rate. Let's say Larry is 30 years old, and he starts putting $5,000 per year into an account that gains 6% compound interest. At age 65, he'll end up with $557,000 for retirement. Now, if Larry had waited until he was 40 to start investing and wanted to end up with that same amount, he would have to put over $10,000 per year into that account. At age 50, the contribution would have to be just under $25,000 per year. So what did we learn? Procrastinating is the most damaging thing you can do when it comes to your retirement savings. But if you've been procrastinating, don't despair, repair. There's still time, and the best time to start planting that seed is today. For this educational video and others like it, visit alliancegroup.academy.
Very fascinating. Time is critical. If you forget everything else that I teach you in this course, I would hope you would remember that. The first example was incredible. The guy only contributed money to a retirement plan for 7 years, okay? Whereas his brother contributed for, 40 years practically. And the first guy actually ended up with more money saved at retirement time, all right? It is so important that you start early. Start early. That is critical, because the longer it can be there and continue to compound interest, you will get more money. I found this one, the math behind this one is really amazing, and I just could not resist. We've got to talk about this. You're at a party, you have one too many. As you walk out the door and consider your situation, you realize you could let your car sit and you could simply walk home. It's only about a mile, all right? It's not because you're afraid of getting caught drunk. Statistics show there's only one arrest for every 27,000 miles of driving drunk. So it's not that you're afraid of getting caught. You're afraid of hurting yourself by getting in an accident if you drive when you had one too many, all right? So should you walk? Okay? 1 out of every 145 miles driven is drunk driving, or there's 21 billion miles of drunk driving every year. 13,000 die in alcohol-related deaths, and there's 1,000 drunk walkers die every year. So should you drive, here's the number of people that die in alcohol traffic accidents. Here are the people that die when they walk, okay? So should you drive or should you walk, okay? Americans walk about a half mile a day, 237 million Americans, 16 years of age or older, or that translates to 43 billion miles walked. 1 out of 140 miles are drunk walking. We're gonna assume the same amount of drunk walking and drunk driving, 1 out of every 140 miles, okay? The math shows that there's 307 million miles walked drunk. 307 million miles walked drunk each year. So I'm going to take 307 million miles, 307 million miles. That's a 307 with 6 zeros. I'm going to divide by the 1,000 people who die from drunk walking. And I get about a number of 307,000. Okay, that's 307 miles per person, per death. Okay, 307,000. Remember that. Let's do the other one. Take your drunk driving miles, 21 billion, which is a 21 and 9 zeros after it. Okay, divide that by the 13,000 people that die and get the number of miles per death for driving. It is 16 million. And what was our other figure? 307,000, right? Divided by 307,000 gives me over 5 times. Did you catch that? There's over 5 times as many, okay? Or the likelihood of being hurt is 5 times more likely if you walk than if you drive, okay? 5 times more likely because there are 5 times as many miles for the driving. It's safer. Now, let's be very, very clear about this. I want no misconceptions, okay? You are 5 times more likely to die if you walk home than if you drive, okay? But if you drive, there's a good likelihood you could potentially hurt someone else, all right? But I just want you to be clear about this, all right? 5 times more likely to die if you walk than if you drive, all right? Which is astonishing. And not that I'm encouraging you to drive drunk. I'm not, because I'm afraid you might hurt somebody else. But I wanted you to see that statistic. All right, so let's get back to chapter 3. Okay, this is men's basketball team. We have taken 2 samples from the men's basketball team. Here they are. Here's the first sampling of heights. Here's the second sample of men's height. We want to find mean, median, and range. Mean, median, mode, and range for each. Okay, so I have the first, and I have the second. Okay, so the mean, I'm going to have to add these up. Okay, so it's 72 plus 73 plus 2 76s and a 78 equals divided by 5 equals mean, X bar is 75. Second one, 67 plus 72 plus 76 plus 76 plus 84 equals, divided by 5, is X bar in a second. 75, same mean. Median, if you put them in order, they are in order. 76 is in the middle. Median, 76. Put these in order. 76, median, 76. Can you all see that pretty good? Yeah, it's pretty close. My marker is slowly fading. Mode is 76 for both. Mode, one used most often. How about the range? The range from the smallest to the biggest. The range here is 6. The range in the second one, 67 to 84, is 17, right? 17. Now, if you look at this, everything is the same except the range. The range shows how the data is spread. You see here, there's not very much spread. It's only from 72 to 78. Here, it's from 67 to 84, okay? A much bigger spread. We should have a name for that. We should have a description of that. And here it is. It's standard deviation, measures the variation by how far observations are from the mean, okay? Today we're going to be talking about how can you find the standard deviation, the measure of that spread. You would guess, and you would be correct. The standard deviation, the measure of spread for team 2, the second sample, should be bigger than for the first sample selected. Okay? All right, let's talk about how you find standard deviation. Now, before we go any further, you can, on any decent scientific calculator, okay, you can do standard deviation. All right? I'm not fighting you. You can do that. But for chapter 3, I always want to see the work. All right? You don't show me the work, you don't get any credit. You don't show me the work on the test, it's going to be marked wrong. Once we get past chapter 3 and you understand standard deviation and how you crank it out and how you do it, then I'll free you up and you can use your calculators to do standard deviation. But bear with me throughout chapter 3 or it will not be pleasant. Okay? All right, let's talk about how you find standard deviation. Make a chart. This is what I want to see when you're doing it. So we're going to make a chart, and we're going to have X column, the X bar. Then we're going to have the X minus X bar squared. All right? So let's talk about that. For the first one, we have 72, 73, 76, 76, 78. Okay? The mean we got was 75 for both of them. Now, what this is, when you subtract these two, you get the distance between them. Now, if you take 72 minus 75, you get a -3. When you square it, it's positive anyway. Okay, negative times a negative is a positive. So it really doesn't matter. I have it written this way, X minus X bar. I really don't care which way you subtract. I don't care if you do it forwards or backwards, because when you square it, it'll always be positive anyway. So this is 3 squared is 9, 2 squared is 4, 1 squared is 1, 1 squared is 1, 3 squared is 9. Okay, add these up, 13, 14, 15, and 9 is 24, right? Yep, so I get 24. When you subtract and square them, you add those up, okay? Then you divide by n minus 1. So I'm going to divide by 4 and take the square root. So for my first sample, the standard deviation, 4 into 24 is 6. So I want to take the square root of 6, and I get 2.45. So the first one is 2.45 for the standard deviation for a sample. This is for a sample, okay? Next one. Next routine is 67, 72, 76, 76, 84, okay? Distance here is 8 squared is 64, 3 is 9, 1, 1, 9 is 81. Did I do that right? Yep, okay. Whoa, no. Yeah, 9 plus 75 is 84. Okay, so let's add these up. 64 and 10 is 74, 75, 75 and 81 is 156, I think. 75, yeah. 156. You want to divide by 1 less and take the square root. Divide by 1 less and take the square root. So I'm going to take 156 divided by 4 is 39 and take the square root, and I get 6.24. The second one is 6.24. And remember what I said when we started here. There is much more spread here in this group. I'm betting the standard deviation is going to be bigger for this one than it is for this one, 6.24 as compared to 2.45. That is how you find standard deviation. That is what I want to see on your homeworks and also on the test, okay? Couple of thoughts on standard deviation. Standard deviation is the amount of spread, is the average amount of spread on the data. Look at the bottom of page 107. This is really interesting. So try to bear with me and find this page, whether it's in your textbook or on the PDF. Bottom of page 107, you have 2 sets of data, data set 1, data set 2. You should be able to see that the amount of spread is much, much more in data set 2 as compared to data set 1. Would you all agree with me on that? Okay. Down at the bottom then, it gives you the standard deviation of the samples. Notice the standard deviation for the sample is a small letter s. Small letter s. We will come back and talk about this later. But standard deviation on a sample is a small letter s. Okay? Because we're eventually going to do standard deviation on a population, and it's different. Okay. Now, if you take those data in data set 1 and data set 2, turn the page and look at the dot plots at the top of the next page. Look at data set 1, the very top one. Do you see how the dots are clustered in fairly tight to the mean, which was 50? Okay. And data set 2 has the same mean of 50, but look at the dot plot and the way it's arranged, spread out, because the standard deviation is much higher. Okay? Really shows that vividly. Now, there are 2 formulas you can use to find your standard deviation. If you don't do it this way, you would have to use the computing formula on page 106. Down at the bottom of page 106, there's something called a computing formula. Okay? Or you can do it the way I've shown you here. This is called the defining formula, all right, which is found on page 105. I honestly think this is the easiest way, all right, but it's up to you. But however you do it, make sure you show me the work. All right, now, one interesting thing when we're talking about data, and we're still thinking about bell-shaped curves, data, okay? Almost all observations will lie within 3 standard deviations from the mean. You can take that one step further, and it's called the empirical rule. This is extremely noteworthy. Let me tell you, within a week, you'll have all these memorized, okay? When you have a bell-shaped curve, 68.26% of the data lie within plus or minus 1 standard deviation on either side of the mean. 95.44% of the data will lie within 2 standard deviations on either side of the mean. 99.74 will lie within 3 standard deviations on either side of the mean. I want to jot those down so that as we do problems here, hopefully 68.26%, 95.44%, 99.74%. Okay? All right. Oh, yes. These are my favorite kind of problems. I love these problems, and I hope you can do them. Suppose your subway commute is usually 30 minutes. That's going to be your average. That's the mean. That's X bar. A standard deviation of 5 minutes. Okay? We're going to assume that the curve is bell-shaped. I really think it's helpful to draw pictures in these. So here we are, and here is 30, the mean. Everybody see that okay? Okay? All right. 68.26% of the time, your commute should be what? We know that 68.26% of the data is within plus or minus 1 standard deviation on either side, plus 5 minutes or minus 5. Would you agree with me, right? This is 68.26% of the data, okay? Plus 5 minutes, the standard deviation, 35, minus 5. From 25 to 35, you ought to have 68.26% of your commutes are within that time interval, from 25 to 35. 95.44% of the time should be within 2 standard deviations. 2 5s would be 10 below 20 to 10 above 40. So from 20 to 40, you ought to have 95.44% of all commutes are between 20 and 40. What percent of your trips would be less than 25? Now here's where it gets really dicey. Let's go back to this picture. This group in here was 68.26. The whole time of your trips, all of them would be 100% or 1, right? So if I take 100%, 100 minus 68.26, I found 31.74 would be trips that are below 25 or above 35. Are you with me? This is 68.26, so 100 minus this will give you the outside part. We don't want below or above, we only want below. So due to the symmetry of this, we're going to divide that by 2 and get 15.87% of your commutes would be less than 25 minutes. Okay, this is where it gets a little tricky. What percent of trips would be more than 45? Let's do another picture. Do it this way. If it's more than 45, this is 15 up. Let's go 15 down. 45 and 15 to 45. Wouldn't you agree with me? 15 to 45 is 3 standard deviations on either side. 3 5s make 15, 15 below, 15 above. Yeah. 3 standard deviations is 99.74. Yes? Okay. Do the same thing. Take 100 minus 99.74. I get 0.26. Okay? 0.26. So I only want above 45, so I got to divide by 2. I get 0.13%. This is not even a whole percent. It's 0.13%. Okay? Hardly ever going to happen that you're going to have a commute more than 45. 99.74% of trips would be within what times? We already did that, 15 to 45. What percent of trips are more than 40? Let's do it again. Erase, erase. Let's go back to 40 right here. 10 above, let's go 10 below. If you go 10 above and 10 below, wouldn't you agree with me that that's 2 standard deviations? 95.44 is here. Do the same thing. Take 100 minus 95.44 equals, get that answer, and you only want more than 40, so you want half of that, divide by 2, is 2.28%. Only 2.28% of trips should be more than 40. Okay? Oh, it's great stuff. These are so much fun. Oh, you're going to be begging me for more? What is this? It's the new keyboard for the Stat Lab. Once you learn how to use it, it'll make computation of the standard deviation easier. Quite a keyboard. Homework, some problems in the book. And then the Shy Sam problem down at the bottom is the same kind as those problems we just got done doing with the commutes. Great stuff. You're going to love these.